Hello everyone, Mark the Future here, and today we're going to be going over some AP Physics 1 practice questions from past years. Specifically, these ones are from 2018. 2018. This is question 1 and question 3. Uh, so let's get into it. So question 1 here is first giving us this little diagram of a spaceship here. And it's saying a spaceship of mass m in a clockwise circular orbit radius r around the Earth, as shown below. The mass of the Earth is me. In the figure below, draw and label the forces, not components, that act on the spacecraft. So, let's talk about what's going on, what's going where here. Well, we know that the force of gravity is going to be pointing inwards. So, F, G. But is there anything else that we have? Let's think about it. There's really nothing else. So, force of gravity is the only thing we have going inwards, and that's it. So then part B is asking us to derive an orbital period t for in terms of little m, big M, and r. And this is actually one of Kepler's laws, but if you don't have that memorized, I'm going to show you how we can get to that. So the first one we're going to start off with is our force of gravity and our is equally our centripetal force. So we are going to have big G, me, little m over r squared. It's going to be equal to mv squared over r. What we're doing here is we use to solve for the velocity, and then we're going to plug it into a different formula to end up getting the period. And you'll kind of see as it comes together. So this should be capital R. So what's going to happen is uh, this will these will cancel, this will cancel, and we're going to be left with v is equal to the square root of big G, the mass of the Earth, over the radius. Let me put this here. And now we need to talk about how can we figure out the period, so the time it takes to make one full rotation. So let's think about this. We know that velocity is equal to distance over time, right? Well, what's the distance that we're traveling in this case? It's 2 pi r, or in other words, the circumference of the orbit, right? What is the time that we are trying to find it in? The period, capital T. And this formula should look somewhat familiar to you otherwise in your gravity unit. So, if we have the velocity, which is our square root of big G, the mass of the Earth, over r is equal to r, what's it called? R 2 pi r over t, then what we can do is we can flip these. So we could have the period is equal to 2 pi r over the square root of g, the square root of g me over r. So from here, this may not look like Kepler's law, but once we do a little work to it, you'll see. I don't know if you can leave it in this format on the answer key. They don't leave it in this format, but they kind of simplify it a bit more. But basically, they square everything to get rid of this radical right here. So they do t squared is equal to 4 pi squared r squared over g me over r. This r will go there. So that's going to be t squared is equal to 4 pi squared r cubed over g me. And this should start looking a bit familiar, as this is Kepler's law, one of his laws at least. And if you want, you can square everything, but you don't really need to. So that's that part. So let me just erase this get it out of the way. A second spacecraft of 2M is placed in a circular orbit with the same radius r. Is the orbital period of the second spacecraft greater, less than, or equal to the orbital period of the first one? So let's think about this. Let's think about, well, we just solved the orbital period here. That was this. Does the mass of the spacecraft play any role into our orbital period? No. The radius matters. The mass of whatever we're orbiting matters, but not the mass of whatever actually is orbiting. So what's going to happen is this will be equal to, and that'll be because I'm not going to write it out. I'm just going to say it because my handwriting is terrible. we're just going to say that the mass of the spacecraft plays no factor in the orbital period of the spacecraft. Of the orbital period of the spacecraft, yeah. So, the next question is, the first spacecraft is moved into a new circular orbit that's a radius greater than r, as shown in this figure below. Is the speed of the aircraft in the orbit greater than, less than, or equal to original speed? So let's go back to this formula right here, what we had velocity or speed. And let's see what it's in terms of. It's in terms of g, the mass of the Earth, and the radius of orbit. So if this radius of orbit is going up, that means that this is going down, just because they are inversely proportional, which means that the speed of this has to be less than. And that is why we just said, because uh, as the radius here goes up, this whole quantity on the right will decrease, this whole quantity, which means that the velocity will decrease too. So, that is that whole question. So, see, it's not terrible. Like, if you have a decent understanding of what everything is, it's not too difficult. You kind of just have to know how to play with your formulas a little bit sometimes. But yeah. Okay. Let's move on to this one. Let me move these out of the way. Let's move these here. So, a disk, as shown it above, spins about an axle at its center. A student experiment reveals that while a disk is spinning, friction between the axle and the disk exerts a constant torque on the disk. At t equals 0, the disk has an initial counterclockwise positive angular velocity. The disk later comes at rest at time t equals t1. The grid below, sketch a graph that can represent the disk angular velocity as a function of t from t equals 0 until the disk comes to rest at t equals 1. So, let's think about this. Friction here, we have it. And it's gonna be exerting a constant frictional torque, like it says right here. Which means that we know we're at rest here, and we know we're starting here, and if it's a constant decrease, we just know it's gonna be a straight linear line. There we have it. Now, when it comes to the angular acceleration, we know that since this is a straight line, this is a linear line, that means this just has to be a straight line right here. Not a constant, but like a zero slope line, because the moment that this angular acceleration has a slope, that will start to mean that your angular velocity graph will start curving. But yeah. Okay. Let's go down to part B, where the magnitude of the frictional torque on the disk is T0 or tau 0, deriving the equation for the rotational inertia of the disk in terms of tau 0, omega and T. So, hopefully your net torque equation is coming to mind. So your torque is equal to I alpha. So basically, our net torque here is tau 0, and it's equal to I, which we're solving for, alpha, which, in case you are forgetting, I hope not, is omega naught over T1. Then, tau 0. We just divide by omega naught over T1, and we will have a simplified version of tau 0 T1 over omega naught, which is equal to I, which is our answer. Um, but yeah, so if you're wondering why this isn't omega final minus omega initial over T final minus T initial, I want you to think really quickly. Omega final is 0, so this gets crossed out. So it's just negative omega naught, basically. And T initial is 0, so this becomes crossed out. So this is going to be negative omega naught over TF. The reason why this doesn't matter, and the reason why I didn't actually put the negative here, is because omega, remember, in our graph is negative. So we're actually going to have like something like negative omega naught T1, basically. And those negatives will cancel out, basically. So that's why I didn't include it before. So now part C. In another experiment, the discus again has an initial positive angular velocity omega naught at t equals 0. And at the time t equals 1/2 of t1, the student starts dripping oil on the contact surface between the axle and disc to reduce the friction. As time passes, more and more oil reaches the contact surface, reducing the friction even farther. So now we're asked to repeat and graph this again, basically. So the first part of this is easy. We know that before T1, before 1/2 of T1 is the exact same. So we know that we're at constantly decreasing, basically, until we get to this stage right here. So constant decrease. And so that's why we know that this is a constant right here. And now, what happens? Well, we start dripping oil, and now the torque, the magnitude of it as time goes on, decreases. So if the net torque is decreasing, so that means alpha has to be decreasing also. So that means alpha will constantly decrease, something like this, which means that your angular velocity, if your angular acceleration has a slope, your angular velocity is going to be a little bit curved. And it's going to follow something like this. It doesn't have to be as parabolic as I drew it, but it has to be. You have to make it somewhat parabolic just to make sure your grader can distinguish, basically. So that's how we do that part. And then part D. A student is trying to mathematically model the magnitude tau of the torque exerted on the axle on the disc when the oil is present at times t is greater than 1/2 t1. The student writes down the two equations, each of the following, which include a positive constant, c1 or c2 with appropriate units. Which equation mathematically models this experiment? So look at each equation and kind of just think about it real quick and try and figure it out for yourself, decide. And if not, I'll explain it in a second. So hopefully you tried it out. Maybe you got it, maybe you didn't. But hopefully, the answer is equation 2. And let's talk about why. Let's think about this. As time is going on with our as time goes on with our experiment up top here, we see that our angular acceleration is dropping. Our torque level is actually dropping right now. So that means time and torque have an inversely proportional relationship. And let's look at what our equations are showing. So this is showing that for the first one, that torque and time are directly proportional. As the time increases, so will torque. And that's not the case we have here. We have it that as time is increasing, the torque is decreasing, which is why equation 2 makes mathematically more sense. And what I said is exactly why the equation 2 is plausible and why equation 1 is not plausible. So I hope this kind of helped you guys understand it a little bit. The AP test is definitely a bit scary, but I think you go into it with prep, you study, and I think you'll do great. But hopefully this helped you guys. Have a great day, and let me know what you guys want next.